some information about last time talk. So you remember we talked about ideal triangles, and we said that there's essentially one ideal triangle in the hyperbolic space. This is because, I mean, one reason is that because the three angles are zero, so there's only one triangle with three angles equal to zero, and so this one or this one here, they are all isometric. So when we work on one ideal triangle, we are working on any ideal triangle. The space of ideal triangle is only one point. If I take other figures in the hyperbolic plane, like this one, this is a triangle with two vertices at infinity and one vertex in the hyperbolic plane. So there are many of these, right? There are many of these which are not isometric, and they are all parametrized by, well, by the angle. For a triangle whose two vertices are at infinity, the only parameter is the angle. So if I take any angle in the hyperbolic plane, I extend these sides. I have only one way to extend these sides, and another triangle here with the same angle. I have only one way to extend these sides. If the angles are equal, then this one I can superpose it with this one. You understand this? So I'm saying this for several reasons. One reason is that okay, this is so. If I take a triangle with two vertices at infinity. Now this is more complicated. There are two parameters, right? And so I have a space, a two-dimensional space of meaningful structures, geometric structures. I have a two-dimensional space, and I can study the geometry of this space. I can ask, for instance, so this is another one here. How do I construct best Lipschitz maps between this triangle and this triangle? This is a good question. See, you have to. You have to. I mean, there's some amount of work here to answer this question. The more difficult question, for which I have no answer, is the space of triangles in hyperbolic space. This is a three-dimensional space. What is the best Lipschitz map between this triangle and this triangle? So I have a space of hyperbolic triangles. I can define a distance between two hyperbolic triangles. This distance I can study. This is a three-dimensional space. Now this distance is complicated. I think it's very complicated because I thought a little bit about it with some co-authors. We didn't find any interesting result. Whereas, as I told you, we have written several papers on the space of Euclidean triangles. On the space of Euclidean triangles, we have some results. In fact, we have a metric. We can describe the geodesics. We can describe the isometries of this metric. We can describe the infinitesimal structure and so on. But for the space of hyperbolic triangles, I don't have any interesting results. So this is a problem where one of you, if he or she works day and night on this during 1 or 2 years, you will have some results on this. Okay, so this was a side thing. This is not the reason why I started talking about ideal triangles. Now I take an ideal triangle. Here, as we said in the hyperbolic plane, I can cut this this cusp here, this edge at infinity, the two geodesics converging to this point at infinity. I can cut them by a geodesic which is perpendicular to it, right? You remember the geodesics are the pieces of circles which are perpendicular to the boundary. So if I take the circle symmetric with respect to this point, then it will be perpendicular to these sides. Okay, so I can do this. I can do this for every one of these triangles. And I can forget now about the pieces which are outside my 3 new geodesics. 1, 2. Okay. So what I get here is a quadrilateral with 6 right angles. In the Euclidean space, it does not exist. Quadrilaterals with 6 right angles do not exist in. I mean, it's easy it should be something you know how to prove. So I have this figure here. 1, 2, 3, 4, 5, 6. Which is I said quadrilateral, right? It's not a quadrilateral, it's a hexagon. Hexagon with 6 right angles. And there's a lot to say, in fact, about these hexagons with 6 right angles. There's a space of hexagons with 6 right angles in hyperbolic space. It has a metric, it has a structure, and so on. And there's an interesting. I mean, this is very useful to know the properties of these hexagons with six right angles is very useful. It's one of the most important things in plane hyperbolic geometry, and this is what I will start to. To study today, and so there are several. Well, they are called trigonometric formula for this kind of. In fact, trigonometric means it's an abuse of language. When you say trigonometric, it means 3 sides. It means for the triangle, 3 sides. But here it's more general than 3 sides. It's trigonometric formula. Just the meaning is that they give you relations. So if I have any figure in the hyperbolic plane, you have angles, and side, and a trigonometric formula will give you relations between angles and sides, right? Like in triangles. But here, the hexagon has only right angles, so the trigonometric formula will give you relations between the 6 sides. So this is what I want to start with. So can we now put this? Yes. Okay, oh, sorry. Where? Ah, this. Yes, okay. So this is not very, very clear. In fact, I took this picture this morning with my phone. I don't know why it's blue, but okay. So before telling you about trigonometry in um, uh, right-angled hexagons, I want to tell you a few things about trigonometry of triangles. So I drew here 3 triangles. When I draw the triangle a little bit fat, you know, it means that it's spherical. When we draw it with straight lines, it means it's Euclidean. And then the hyperbolic triangles are always represented like this because the angle sum is less than 2 pi. So they are the angles, are narrower than the Euclidean angles. Okay, so I have an example here of a trigonometric formula, which is the law of sines. So we have big A, big B, big C, the length of the sides, and then alpha, beta, and gamma. Here it should be gamma. This should be gamma, this should be gamma, this should be gamma. Alpha, beta, and gamma are the angles. The Euclidean law of sines, which you know is A divided by sine A equal sine alpha equals B divided by sine beta equals C divided by sine gamma. You know this, right? You know this? Okay. I'm not going to prove the spherical and the hyperbolic laws of sine, but they are not difficult to prove. They are rather easy to prove if you have a little bit of experience with hyperbolic geometry. But the thing I want to highlight is that you keep the same formula, but you replace the sides by the sine of the sides in the spherical case, and by the hyperbolic sine of the sides in the hyperbolic case.
Are we thinking A as a radian and then evaluate
Radians?
Yes.
Yes.
So sine A, like when we evaluate sine,
Yes.
you need to think of it as radians or degrees.
Radians. Radians, yes. So it's so I have 2 remarks on this. So this is something which is well known, but I have 2 remarks. My 2 remarks. Yes, my 2 remarks are here. So the first one is something which you can notice is that okay, I cannot see. If you take the Taylor development of the sine of the sinh, that is for, as I said, for infinitesimal triangles where the sides are infinitesimally small, you get the Euclidean formula. And this is this is a consequence of the following fact, is that hyperbolic geometry and also spherical geometry are infinitesimally Euclidean. You see, this is an important fact. To know a geometry, to the behavior of, you want to know the behavior of lines of geodesics and so on. It's sufficient to know the trigonometric formula. This trigonometric formula, because they give you the geometry of the triangles, the big or the small triangles, knowing the trigonometric formula gives you, in principle, all the information you need to know about the geometry. And this tells you this fact, which is a special case in any Riemannian manifold. Well, if you know about Riemannian geometry, the geometry is infinitesimally Euclidean. This is a property which I want to highlight. The second thing, yes.
What do you mean by infinitesimally Euclidean? Do you mean the local isometry? I mean,
when the triangles, no, it's the behavior of the geodesic, the behavior of the triangles.
straight line, right? I mean,
Yes,
straight line.
yes. So you see, yes, I don't want to. In a Riemannian manifold, there's a norm on each tangent space, which is a Euclidean norm. Okay, so locally it's Euclidean. The first metric, which I will explain, is not Riemannian, and this is one point I will make later. There's a let me write it here. For Thurston's norm, for Thurston's metric, so this is a Finsler metric defined locally by a norm which is not Euclidean. So this is one thing we will study later. Okay, the second question now, the second remark is a question. So I come back to my formula. You see, so there are natural ways. There are natural ways there are at least there are a few ways to transit between the three geometries. So, for instance, let's say you have the sphere. You have the sphere. You take a bigger sphere, then a bigger sphere with a radius growing to infinity, and this point here. Okay, visually, I mean, you will tell me that the limit is a plane, right? So how can you so this is what I mean by transit between the three geometries. So transit, well, make the trigonometric formula transit between the three geometries. This is I think a question which is very interesting, which you can study. In fact, I have a few. I have some work on this. I think I have 2 papers with Norbert Acampo. The papers, I mean, the title is something like transitional geometry, or something of this same kind. We didn't. I don't think we made we made the transit of the trigonometric formulas. We did not do this. We did. Yes. Yeah. Yes. It's a mistake. Yes. I'm sorry. Okay. So these are my 2 remarks here. Yes. So I said there's a. Sorry. This is another. So there is an analogous. Yeah, I'm saying I put it here. So for hyperbolic geometry, I said last time that there's a formula which gives you the sides in terms of the angles. Right? In Euclidean geometry, you don't have this. The 3 angles do not determine the sides. But in hyperbolic geometry, we have this formula here. It gives you this length here, or the cosh of this length, in terms of the 3 angles. And so I didn't write it here, but the question is, okay, so what happens what happens in this theory of transitional geometry? What happens to this formula? This is something which you can obviously. I mean, you will. There's a analogous formula, as I said, for spherical geometry, where the cosh is replaced by cos. From the previous slides, you noticed that, I mean, there are many formulas in hyperbolic geometry which resemble those of Euclidean, of spherical geometry, where you replace the hyperbolic trigonometric functions by the trigonometric functions. So what happens with this formula when I take infinitesimal triangles? Since we know that infinitesimally, hyperbolic geometry is Euclidean. So what happens? This formula seems to give a contradiction, you know? Okay, so this is a problem for you. And I have a third remark. So something in spherical and in hyperbolic geometry is that there are dualities. There are duality for so people. If you are interested in hyperbolic or spherical trigonometry, there are some dualities. I mean, there's a way to pass between angles and sides. This is for those who are interested. This is polarity. Polarity theory. So polarity theory in spherical geometry means more or less that for any given triangle, a spherical triangle, you have another triangle where the sides of the one are the vertices of the other one, and vice versa. The vertices of the first one are the sides of the second one. So this is, I'm saying it very roughly. It's not exactly like this, but this is polarity. It's polarity between, say, between angles and sides. You have to be careful sometimes because here there's a plus sign, here there's a minus sign. This is also part of the theory. Yes, so this is something that you should know also. I mean, when you study hyperbolic trigonometry. So this is what I wanted to. I'm not going to. So we need hyperbolic trigonometry. I don't want to give all the formulas. I think they are not interesting. I never remember the formulas, but I know that they exist, and I use them several times. I have to look to my formulas. So this is something you might want to learn also. The fact that there is a duality between formulas. Okay, so next. There's also, this is important also. This is important. So let me just, before I forget, let me mention that I learned almost all these things in Thurston's notes, the geometry and topology of three manifolds. In fact, the notes are on three manifolds, but the first there are some chapters on surfaces. This is from chapter 2. Chapter 2 is hyperbolic trigonometry. And he does, at the same time, the spherical and the hyperbolic trigonometry, which I think is the correct way to understand things, to do things. You have to do them together. So if you are interested, you look at this. These are available on the internet, in fact. Okay, so so this is another law of sines. You see, I learned this also from Thurston's notes. So I have, so we come here to right-angled hexagons. I started with right-angled hexagons. So this is trigonometric formula for right-angled hexagons. So you see, it resembles. So if my picture I have drawn here alpha and beta small, and I could draw them very, very small, and then they became the alpha, beta, and gamma become like angles. Okay, just to tell you that this is another law, and then you get the law of sines, which was in my previous slide. Okay. But this law of sines is important because it, you see, it tells you that you can get the side A. You can get the side A from three other sides, which are alpha, B, and beta. Alpha, B and beta. From the three sides of this right-angled hexagons give me this this other side A. And this is a general rule. In fact, it's not only this formula. Let me write it here. In a right-angled hexagon, any three sides determine the rest. Determine the rest of the sides. I already told you, I think, today that this, yes, huh? No, not up to scaling. So this is hyperbolic, right-angled hyperbolic hexagon. You cannot scale. In fact, there's no scaling in hyperbolic geometry. You can scale only in Euclidean geometry. So let me make a picture here, another picture. Yes, we take this model, okay. Okay, so I take a small, well, I take a length, certain length, part of I want to build a right-angled hexagon. I start with some yeah, sure. All the sides and all the segments I'm taking here are geodesics. So I want to build this. So suppose I know this is my hexagons. This is my hyperbolic hexagon, and I want to show that these three sides determine completely the hexagon. Yes.
Consecutive sides, right? Otherwise,
this is what, no, consecutive or not.
A alpha and beta, suppose there is C or gamma, you have choice.
Yes, I know, but this is this formula, but there are other formulas. I'm not giving them all. I think I will give them later because we will need them, but this is one. And I'm saying here, you see here, wait a minute. B alpha and beta, B alpha and beta are not consecutive sides.
Yeah, that's what I meant.
Yes.
If you choose A alpha and B.
Yes, right. Now I'm choosing consecutive sides. I'm doing the same, but for consecutive sides. So this is one, and then the other one. Okay, it has to be perpendicular, and I know the length. Okay, and this is the third one. So I know these three. And now I say that I know the hexagon. The right-angled hexagon is completely determined. Why? Because, okay, I know that this other side lies on this geodesic. Which is perpendicular, and it is unique. Okay? The other side here also lies on this geodesic, which is perpendicular, and which unique. It is unique. And now something which I didn't tell you, but you must know in hyperbolic geometry. In hyperbolic geometry, when I have, let's draw it here. When I have two lines, 1 and 2, there's a unique line which is perpendicular to both of them. A unique geodesic which is perpendicular to both of them. Okay? This is one of the things you need to know in hyperbolic geometry. So So, and this is, I mean, you can think of the fact that there's a shortest line between them, and you extend this shortest line, and you find this geodesic. Okay, so here these two sides have well, a unique geodesic joining them. And so these three sides determine uniquely the right-angled hexagon, right? Okay, so this is, again, the fact that the space of right-angled hexagons is a three-dimensional space. Yes, so this is, I said, this is first, and this is what I just explained. Any right-angled hexagon, any three sides determine the others. This is in Thurston Notes, chapter 2, which is called Elliptic and Hyperbolic Geometry. Elliptic, he means the sphere. This is now a question for those who like this kind of things. When Thurston's notes appeared, it was in 1978. I mean, maybe I need to tell you because you don't know about this. They made a revolution, a real revolution in the topology, and in geometry. And it took a few years to people to start to understand these notes. And I mean, there are hundreds of PhD theses which were written from these notes and so on. So it was this question of best Lipschitz maps was not. I mean, Thurston wrote about it in a paper which I told you about last time, about the same. No, it was in '85, but. I mean, this West Lipschitz maps paper remained mysterious, in fact. And now people rediscover this paper, and you can read Thurston's notes thinking about West Lipschitz map. This is why I put this in bold-faced letter here. Study Lipschitz map between right-angled hexagons, but this is between right-angled hexagons. In fact, I did it with my co-authors. I will give you the reference. But study between other pieces of hyperbolic. Yes. Yes, with the smallest Lipschitz constant. I will talk about this many times. In fact, this is what I. So Lipschitz constant. So. With any manifold, in fact, the work. Thurston's work is on surfaces. Many works have been done recently on different kinds of surfaces, hyperbolic, Euclidean, spherical, whatever you want. And there is a small work, in fact, I think by Guerito and Cassel and somebody else. Three people who considered best Lipschitz maps between some three manifolds. Yes, the theory. I mean, the theory is not easy, even for the simplest cases. So this is the Lipschitz. So you have a homeomorphism. You have a homeomorphism. You have a Lipschitz constant of this homeomorphism. And you want to study existence and uniqueness, and then the geometry of the maps between the two objects, which minimize this Lipschitz constant. There's a very long paper which appeared recently. In fact, I know it because I wrote a review of this paper by Daskalopoulos and Uhlenbeck. a thick paper, maybe 100 pages, which appeared in Journal of Differential Geometry, where they study best Lipschitz maps from a surface to the circle. I think nobody had this idea before. So this is what this is. I mean, no. Yeah, right. Yeah, right. Just the circle. I mean, I mentioned last time that I studied Lipschitz maps between Euclidean surfaces, and then I said that geographers study best Lipschitz maps from the sphere or parts of the sphere to the plane. They didn't know they were doing best Lipschitz maps, but they studied this, in fact, heuristically. And then there is a paper written in the 1950s by John Milner. In fact, I think it's his first paper. Maybe I will talk about this. It's called On Geographical Maps. And he talks about best Lipschitz maps from the sphere to the plane. Before Thurston wrote on this theory. Yes. Yes. Okay, so okay, this is Thurston's paper, which this is my old slide. Duality. Okay, so now there are a lot. So this is a right-angled hexagon. This is a right-angled hexagon. This is a right-angled hexagon. This is so when you study this is also a right-angled hexagon. You remember we talked about best Lipschitz maps between. Well, we talked about Lipschitz maps, not Lipschitz maps. This is the basis. Lipschitz maps from the ideal triangle to itself, and we said that we have this. It uses this foliation and so on, and then we send one of these pieces of circle to the other one, and so on. Remember this? So this is, and I explained to you today. I tried to explain that ideal triangle is a kind of a degenerate right-angled hexagon. When these sides tend to zero, then you have when the length becomes zero, you get ideal triangle. So this is a little bit more general theory. Best Lipschitz maps between right-angled hexagons. And here, this foliation here, by pieces of horocycles, it is replaced by a foliation by pieces of hypercycles that is equidistant lines from these geodesic boundaries. You see, in hyperbolic geometry, if you take a line, let's say this one, in the hyperbolic plane, and if you take the set of points at distance 1 from this line, this is what I call an equidistant to a geodesic. So it is not a geodesic. It's a line like this, which is called a hypercycle. It has a name. A hypercycle is an equidistant set. A set of equidistant points to some geodesic. So these are all hypercycles until here. So this picture resembles this picture here. And then, okay, you must do more or less. You do the same thing as I explained last time. For ideal triangles, you do this for right-angled hexagons. And then you do this theory. And then I put this in bold letters. There's a space of right-angled hexagons. I said this several times. study best Lipschitz map between right-angled hexagons. This is the problem, and it's. I mean, there are two papers on this problem. One 2012 and one 2017, deforming hexagons and the arc and the Thurston metric, etc. So I put the abstract for each right-angled hexagon in the hyperbolic plane. We construct a one-parameter family of right-angled hexagons with a Lipschitz map between any two elements in this family, realizing the smallest Lipschitz constant, and so on. So this is exactly the problem I said. And my question to you is, for those who want to do the same thing, but not just for, I mean, right-angled hexagons, there are still problems to do here, but the simplest thing is already done. But you can start with right-angled pentagons, the space of right-angled pentagons, which I think it should be more difficult than the right-angled hexagons, but or whatever I have some pictures here. These are quadrilaterals. These are quadrilaterals in the hyperbolic plane. This quadrilateral here, you see, in hyperbolic plane you do not have rectangles, right? You know this. Why? Why you do not have rectangles? I mean, you don't have figures with you don't have quadrilaterals with 4 right angles. Why? Yes, because if you divide into 2 rectangles, and you know that the angle sum in rectangles is strictly less than 2 right angles. So here you have 2 rectangles with the angle sum equal to 4 right angles. This is not possible, right? Right-angled pentagon? It's not possible. Yeah, okay. No, okay. So forget about pentagon. You do heptagons. You do heptagons. Yes, I'm sorry. Yes. Right-angled figures with 7 sides or 8 sides. It should be easier, in fact. Huh? Even sides should be easier. Yes, even sides should be easier. Yes. You know, sometimes I don't know how to count. For me, 7, 18 is the same. All of them are numbers. This is why when people, I write emails to people, and he said, "You said 25th of January, but this is long ago." Okay. Yes. So instead of rectangles in hyperbolic geometry or in spherical geometry, there are these figures called Zachary quadrilaterals. So Zachary quadrilaterals. So this is a figure with 2 right angles, and then equal sides here. These sides are equal, so this angle should be. So this is the analog of rectangle in hyperbolic geometry, or also in geometry in spherical geometry. In spherical geometry, a Zachary quadrilateral would be like this. This angle here should be greater than pi over 2. The thing is that you know, Zachary is someone I think from 17th century or before. These are among the people who studied hyperbolic geometry before it exists. In fact, they said, okay, but if this geometry exists, then then we would have this and this. So among these people is Zachary, who said if this hyperbolic geometry existed, then there would be quadrilaterals with two right angles, and then the two angles would be less than pi over 2. And then he studied this special case where the properties of this special case of quadrilaterals where this side is equal to this side. So this is why we call them Zachary quadrilaterals. So this is one thing. Yes, so I will tell you more about best Lipschitz maps. In fact, this is the subject of my series of talks. So let me see here what I wrote. Generalizations to Lipschitz map. Now, from spherical to Euclidean. From spherical to Euclidean, we talked about this. I mentioned this problem of geography. Right? We want best Lipschitz maps from the sphere, or from part of the sphere to the Euclidean plane. And in fact, I said conversely, you see, there are also these best maps from the plane to the sphere were studied by some mathematicians. For instance, Chebyshev, you heard this name, Chebyshev inequality. So he was interested in the following problem, in the problem of clothing. So you have a piece of fabric, and you want it to cover to cover your head or to cover your so on. I mean, you want to build, and so you are sending something which is Euclidean as a Euclidean surface. You want to find the best way to cover something which is non-Euclidean, which could be spherical, or here you have some points where you have negative curvature, and so on and so on. So this is the problem of Chebyshev problem on fabrics, which I didn't mention here. Yes, I said here applications to geography, to cloth fitting. Brain warping, this is a little bit more complicated. In fact, it has to do, people study brain warping. Warping. You see, when you have some picture, which your eye is, which is in front of you, how does your brain recognize it? Your brain reconstitutes a picture, in fact, right? This is a whole theory in computer vision use this. So this is also where best Lipschitz maps are useful, and so all this theory leads to new definitions of distances between surfaces. So when when I can define, you see, when I can define a distance between two, say, two Zachary quadrilaterals, then I have a metric on the space of all Zachary quadrilaterals, right? And I can ask all the questions I know about metric spaces in this special case. So this leads to new metrics on Teichmüller spaces. One of them is the Thurston metric, which we shall study, which we are studying. And I will explain how these metrics are generally Finsler metrics, they are not Riemannian. And I will recall what is a Finsler metric. So this is part of what, yeah, okay. So before going on, I want to make a few I want to recall a few things. I know that Professor Ridisha yesterday talked about homotopy, fundamental groups, and things like that. And is the metric the spherical law of signs for spherical law normalized in some? No, the metric is not. There's no normalization. No, no. No, but escape the sphere and keep the angles the same while changing. If you want, just take the sphere of radius 1. Yes, just take the sphere of radius 1. This is the question. This is for the first question. The second question: 3 sides determine other sides of polygon. Yes, can we generalize this formula for other polygons? So this fact that the three thank you. This fact that the three sides of right-angled hexagon in hyperbolic space determine the other sides. He or she is asking whether we can generalize to other kinds of polygon. Yes, there are. In fact, there's a book, I think a book by Fenchel. Yes. It contains a lot of many. Fenchel is a great mathematician, in fact. His book was rather unknown until Thurston came with this hyperbolic geometry, and then people started being interested in non-Euclidean geometry. But he wrote this book much earlier, Werner Fenchel. And he has a lot of trigonometric formulas for not only for hexagons, but all sorts of polygons, and with not necessarily right angles. Yes, so there are trigonometry. Just look into this book. Thank you.
So,
yes.
I would like to follow up on this. So, the right-angled hexagon
yes.
came naturally by slicing the infinity points in an ideal triangle.
No, you're right. I said, you're right. So I don't want to start with an ideal triangle. I started with ideal triangle, but this is not a good idea. No. You slice like this. 2 geodesics. Yes. Yes, you're right. Somebody pointed out this. Yes. Yes. Yes.
Can we generalize this, for instance, get a quadrilateral and then?
Yes. I mean, there are many interesting constructions you can do here. Yes. Okay, so I want to. Mike, I don't know how much you know about surfaces, but I want to recall some basic things. Okay, so let me first state some topological facts. So first, the classification of what? Classification of surfaces, and I want first compact, oriented, and without boundary. Who knows about this? Who knows the classification? Who does not know the classification? Okay, so I will make I will tell you just a few things about it. You don't need to know a lot about this. So I will make some pictures. This is topological, right? The sphere here is not equipped with any metric. It's not the spherical metric. So this is also the sphere, right? It's the same surface topologically, okay? So you have the sphere, and then you have this is the torus. You have the sphere. You have the torus, and then you have this genus 2, and so on. Genus 3, so this is genus 0. This is genus 1. Yes? Sorry, yeah. Genus 0, genus 1. Okay, so these are the kinds of, these are mostly, not all of them, but the kind of surfaces that we are interested in. This is the topological classification of. So these are all compact, they are oriented, and they don't have a boundary. Then we need the theory with boundary. Let me. It's fine. So if I need with boundary, then I will remove a few disks. I remove a disk from this surface. What do I get if I remove a disk from the sphere? What do I get topologically? What do I get as a what? Yeah, sure. Yes, thank you. So this is the same as a disk. The torus, when I remove a disk, I get something which I cannot, which is not a planar surface. It will be still surface of genus 1. I can remove 2 disks. I can remove 3 disks. I can remove 4 disks. So now you know what is a compact oriented surface with boundary. It's obtained from one of these surfaces by removing a certain number of disks. The theory with boundary is important in this theory, which this is why I'm insisting on this. So am I removing open or closed disks? Yeah, I'm removing open disks so that the result is a compact surface. So you must so with or without boundary. And one last thing, in fact, sometimes I can remove. Sometimes I need to remove some. Yeah, okay. In fact, sometimes instead of removing an open disk, I want to remove a point, which is homeomorphically the same, but geometrically it will not be the same. Okay, I will say this later. Anyway, so this is the classification. This is the classification of surfaces.
Surface is punctured and surface with a boundary or same thing.
It could be with punctures and with boundary. Both things are allowed in this theory, and you are obliged to work with both things. You see, you are obliged also to work with, as I said, the ideal triangles will play a very important role. And so how does this ideal triangle fit into this theory? Okay, this is not compact. whereas this is I'm talking about. Well, it will come in the following way, because I will glue two ideal triangles along their edges, and I will get a sphere with what? I will get a sphere with 3 punctures if I do the gluing in the correct way, because if can I get something like this? By gluing two ideal triangles? Yes, yes, the triangles. In fact, it's a picture which I already showed you, right? So here will be an ideal triangle with spiraling along the boundary, and so on. And yes, so this is something we will have to be careful about. So anyway, so now about the. I want to say a few words. So this is topology. This is the topology of surfaces. Now I want to say a few words about the geometry of surfaces. So I will put a metric on each of these surfaces, and I will choose the metric to be the easiest one among I know. So I know just 3 kinds of metrics. I know until now we talked about the Euclidean plane, we talked about the sphere, and we talked about the hyperbolic plane. So I want to put a metric on my surfaces so that it looks locally like one of the metric spaces we talked about. So okay, if my topological surface is of genus 0, then I know I have the spherical metric on this surface. In fact, there is no much to say about the spherical metric if I talk about it like this, because there's only one possibility. It's not. There are many interesting things about spherical geometry, but at this level, there's only one metric I can put here. So this is the sphere. Now on the torus, somebody knows what kind of metric I can put? Yes, I can put Euclidean metric. This is also something you should know. If not, I want you to learn. Yes, S1 cross S1. S1 cross S1. So how do you put a metric on the torus? A metric which looks locally like Euclidean metric. Somebody can tell me?
We take a patch in the torus, I mean a square patch.
Yes.
Then map it to the Euclidean space.
Yes. So your friend here is telling. Okay, he said you can take a Euclidean square. You identify these 2 sides here according to the arrow, and these 2 sides here according to this arrow, and you get something. You must imagine it, because if you imagine it, this is important. If you imagine it as a part of Euclidean free space, you will not think that it is flat, right?
Flat torus is not S1 cross S2.
No, S1 cross S1 is topologically.
No, but
this is
torus is not S1 cross S1 in R3, right?
Topologically, it's S1 of cross S1, as Professor said.
But you are now saying that you cannot visualize it in the.
Yeah, you can visualize it in R3, but not as a Euclidean surface.
So if you identify these up and down two sides, you get a cylinder, and then you identify these two sides, so you're rolling the cylinder to make it wing,
Yes,
like a donut.
yes.
Boundary of donut.
Yes, but what I'm saying is that this metric you see on the this metric which you see in this embedding in the 3 space is not the Euclidean metric. This is just what I'm saying. You must think of it abstractly. So just one more remark about this. If I instead of gluing this, if I glue a parallelogram, I do the same gluing, but on a parallelogram like this, I can, in fact, I can think about the surface which I get. The two are homeomorphic, but are they always isometric? The metric is different. How do you see that the metric is different?
Angles,
No, it's not because the angles. No, the angles do not play any role here because at this point, at this point, the total angle is 2 pi, exactly 2 pi, like a.
yeah, that's true, but the local angle between the
No, because here on this one I would have geodesics which make other geodesics, and this one which would have the same local angle. This is not a reason. How do you prove that? So I didn't tell you. Okay, let's do a simple thing. So this is length 1. This is length 2, and this is length whatever length 1 is here. How do you prove that these two things are not isometric?
Take 2 points and the distance here is different from the distance there.
Yes, but no, you cannot, because what I'm saying is that there is no isometry between these two tori, meaning that these 2 points. I mean, they are not these 2 points here. They are not necessarily sent to these 2 points here. There is no isometry at all. How can you do this? Yes, please. Exact. What he says is correct. They have different area. They have different area, and area is a geometric invariant, so they are not isometric. Now this is very good, but still, okay. Let's make them same area. How do you know now that these are not isometric? This is the important thing, in this theory, because the Teichmüller space, which I'm talking about, I will talk about, is the space of non-isometric surfaces of hyperbolic type, or here it's Euclidean type. So, okay, so what is this space? How can I show that? How can I give example of two surfaces where I'm sure that they are not isometric?
I think there's a loop of length 2 here. There's no loop of length.
No, this is not sure, because I mean, maybe it will, yeah, but let's take it here a little bit smaller, and there may be a loop, you see, of length 2 here, and a loop of length 2 here, you see, so it's a little bit more complicated, So after what our friend says there, we shall consider tori of area 1. So there's this normalization, okay? And then how do we know that one thing which we could look at is shortest geodesic. Shortest geodesic. So, for instance, let me exaggerate a little bit and take one area 1, but like this. You see, and I am gluing this to this, and I am gluing this to this. And you can imagine that, okay, I have loops, I have closed loops, which is very short, whereas here it's not possible to have closed loops which are very short. So in this exaggerated example, I know that the tori cannot be isometric. They are homeomorphic, but not isometric. And again, the Teichmüller space is the space of one of these surfaces. All of them are homeomorphic, but none of them are isometric. And I have to have, I have to give a meaning, or I have to have a method for deciding why are these surfaces not isometric. So, for instance, in this case of the torus.
The length of meridian and longitudinal circle would be major?
Length, no, because length of this. You see here, you will have, as we said before, you will have a very long. The notion of meridian doesn't make sense here. It will have a very long closed geodesic, but here I may have one which is, and then it closes and the same length. You see, and it has a tubular neighborhood, a small neighborhood, which is exactly this one. So here, for the case of the torus, in fact, there is, there's some work to do. There's some number theory here which you have to do, but let me just give you.
What metric are you taking as embedding in R3?
No, just the Euclidean metric induced by the metric on this rectangle or on this. Okay, so let's do this more carefully. I have a surface which is this one, and I want to define a metric on this. I want to put a metric on this surface, and this metric is, I want it to be a Euclidean metric. What does this mean? This means that around each point, I have a small or a big neighborhood. I have a neighborhood of this point, which isometrically, I can see it as a subset of the Euclidean plane. Okay? This is what I mean by a Euclidean metric. Okay, so we said that we want to have a normalization, and the usual, in fact, useful normalization is this one. So space of Euclidean metrics on the topological torus. And okay, we said that there's a normalization. For instance, we don't want to have tori where one is just the multiple of the other, right? There's another. So okay. So the first fact. The first fact is the torus is the quotient of the Euclidean plane. Let's write it here, U for Euclidean plane, by a group two-generator group acting freely and properly discontinuously. I don't know if you explain these words. No, okay. It doesn't matter. It doesn't matter. It doesn't matter. It doesn't matter. In fact, I will explain it. I will explain it with words. You see, this is. I take my plane, the Euclidean plane. I take these two vectors here represent translations. So this, what I mean here is that this point, so the torus, Euclidean torus, is the quotient of the Euclidean plane by the group generated by these two translations. I think I'm complicating the matter here because I don't know exactly what level I need. Okay, so do you understand this group generated by these two translations? Do you know what is a quotient space? Okay, so I have two independent vectors. Let's start with one vector. Maybe it's easier. So you have the Euclidean plane in front of you. You have the origin, and then you have a vector v, which I said it represents a translation. Now I want to. The plane itself is a surface. You understand this, right? I want to find a little bit more complicated surface. This surface will be the quotient of the plane by some translation. So this is only translation by a vector. So each point is identified with its image, the image by this translation. So this is identified with this, and now I'm asking what is the resulting surface? What is the quotient? What is the quotient space? Yes, here they know. There. So I take the plane. I identify any 2 points when they differ by this vector which I'm drawing here. What do I get? So for instance, this line here will be identified with this line here, because any point here is identified with this point, any point here is identified with this point, and so on. And this line here will be identified with this line here, because so at the result, what do I get? Thank you. I get a cylinder. And this cylinder I get is equipped with a metric. In what sense? In the sense that each point in my cylinder Well, originally, it has, when I look around me, I find a part of the plane, a part of the Euclidean plane, right? With all the discussion we had on triangles in the plane, Pythagoras theorem, the trigonometric formula, and so on. I can compute this for all my triangles around me, right? And this is the meaning of the fact that the cylinder is equipped with a Euclidean structure, right? Even the point, even this point here it has a neighborhood which I can continue here because it's identified with this point. So, okay. So now my next question is I can get many kinds of cylinders by changing what? Changing the length of this vector. So the initial vector is this one. Now I make it a little bit bigger. This is my new vector. And I do the quotient by the new vector. I get again a cylinder, right? How do I know that the two cylinders are not the same, are not isometric, that there's no isometry from the first cylinder to the second cylinder? Or do I know this? Again, because the Teichmüller space is the space of different hyperbolic, here it's Euclidean structures, different Euclidean structures. How do I know that these Euclidean structures are different? That I get different Euclidean structures? Yes, we will ask here our friends here. So how do I? Yes. So because for the initial cylinder, there's a there's a shortest loop. He said there's a loop which goes here, and then I come back to the same point. The shortest loop. Whereas for the bigger one, the shortest loop is longer than the first one, right? For the new cylinder, this is the first cylinder. The new cylinder is larger, and the shortest loop is well, I can see it's larger, but how do I prove geometrically that there is no isometry from this cylinder to this cylinder? Isometry means that it preserves distances. Okay, but isometry implies that the shortest loop in the first one will be equal to the length of the shortest loop in the second one. Okay, so I get different kinds of cylinders, by taking this vector longer and longer. And I know they are all non-isometric because the length of the shortest, yes, this is, well, let me write it more. Let me write it more precisely. The length of the shortest loop. I must say something about this shortest loop, because here I have also loops. I have loops which are I can find a loop here whose length is the same as this one. So what do I have to put there?
Not contractible.
Yes, right. The shortest loop, non-contractible. Did you say something about this?
Yeah, contractible.
Because here you see I have this cylinder, and then there's a shortest non-contractible loop, and this is an isometry invariant. The length of the shortest non-contractible loop is an isometry invariant. If I say simply the length of the shortest loop, then the shortest loop, its length will be 0 here. You see, this is the shortest loop. So, yes, non-contractible, that is non-homotopic to a point. And now my other question, the natural questions which comes here. Okay, so these are infinite cylinders. It doesn't really fit into my theory because I said they are compact. The infinite cylinder is not compact, right? But it's important to understand this. So my next question is, okay, so I start with, I have two Euclidean bi-infinite cylinders. Let me not explain everything, but bi-infinite means that okay, it's infinite from this side and from this side, because I could have also a non-compact cylinder where here it's which is open here and infinite from this side, and it will be also a non-compact cylinder. But I want just to simplify, consider the bi-infinite cylinders. I have two bi-infinite cylinders, and my question is, how can I recognize that these two bi-infinite cylinders are isometric or are not isometric? Yes, it's the same thing. So now, if you have followed everything I said, I mean, if you, I will not write a proof, in fact, but this is almost clear by. It is clear from the pictures and from. So they are isometric if and only if the length of the shortest non-contractible loop is the same. Is the same in each of these two cylinders. Do you believe this now? I didn't prove it rigorously, but I mean what I gave is a proof. In fact, in principle, I mean, if you know a little bit of topology, you understand this. Are you okay with this?
You only need these vectors to have same length. The angle doesn't matter anyway because.
Well, no, there's no. In fact, no. This is because the Euclidean cylinder is independent of this construction. I just have two Euclidean cylinders by infinite, this one and this one, and I'm saying that there's an isometry from this one to this one if and only if the length of the shortest loop is the same. And if you want to prove this, okay, you say, okay, right. First, I have to, I consider a shortest loop, and here I consider a shortest loop since they have the same length, then there's a length preserving map of one-dimensional map between this and this. And then you want to know whether you can extend this one-dimensional map to a two-dimensional map, and how much you can extend. And in fact, since both of them are cylinders and by infinite from both sides, then there's no obstruction to extend this map to an isometry between the two cylinders. So I mentioned the word several times, the word Teichmüller space. So what is the dimension of the Teichmüller space of this cylinder, this Euclidean cylinder? It's only one. There's only one parameter, one real parameter that can distinguish by infinite cylinders. Okay, so and then for the torus. For the torus, it's a little bit more complicated. I mean, it is more complicated for the. It is complicated, and it's something which I want you to know. Just okay. Let me write it. Let me write what I said first. In other words, so the Teichmüller space of the bi-infinite cylinder is one-dimensional. Not only it's one-dimensional, but it's, in fact, it is, in some precise sense, it is the real line. No, not the real line, because I want only positive. So, yes, right. So do you write this like this? Because in France you write zero infinity like this, but you use the American notation. You use the second one. Okay. The first one. You use this. Okay. Okay. So it's okay. Okay. So this is a one-dimensional Teichmüller space. Now I want to state, I want to state the same thing for the torus. Now, for the torus here, my surface of genus 1 with no punctures. Putting the punctures will complicate, will give another interesting theory, more interesting. So now, again, this is 1. Okay. Let me say again something about the first case. So I have, so it is the positive real line, and I have a metric on this positive real line, which is the usual metric where this distance between 2 points is the absolute value of the difference. Okay. So now I'm more happy even because it's not only homeomorphic to the real line, but I can put a metric. I have a metric space. The space of bi-infinite cylinders is a metric space. Now the Teichmüller space of the torus. Now this compact surface of genus 1. Can you guess what is the dimension now of this? Yes, you have a question? Yes.
Then take the shortest non-conjectural loop.
Yes.
And take the next shortest non-conjectural loop.
Yes.
Then pack the first shortest non-conjectural loop. Then it will be by infinite cylinder.
Okay, what you're saying is reasonable. So she's saying that on the torus, I want to take the shortest non-contractible loop. This gives me something important, an important invariant. And then she says, then take the length of the next one. If I cut, I get a finite cylinder. It doesn't fit into the theory above. It will be more complicated because before this I said something about by infinite cylinders. But if I cut, I get a finite cylinder. Huh? Yes, but yeah, you are right. It's open, but yeah, I mean, when I said by infinite, I meant the distance goes to infinity from both sides. Yes. Yes, complete. You're right. I should have put complete there. Okay, but you are right. The thing is, the thing you said is very interesting. I'm not completely sure whether it's correct or not. That if you take just the next one, because how do you know that? Okay, the shortest geodesic is the same, and then the next shortest is the same. But how do you know that the third one will also be the same? I mean, it needs a proof. If it's correct, it needs a proof. I'm not sure that it shows that the tora are isometric.
If we try an exaggerated example again.
What?
of this,
If what?
Like with
Yes.
the torus, like if
Yes.
we have an exaggerated torus.
Exaggerated torus?
And then
Yes. If it's exaggerated torus, yes, he's right. Yes. If you take a torus which is like this, then you. But what is true, which I want to emphasize now. What is true? I will complete there, but. So for all these surfaces, forget about the sphere because I said the spherical is not so interesting for this theory. For the surface of genus 1, this is Euclidean. And this is all of these are hyperbolic. In fact, these are obtained as the quotient of the hyperbolic space by some action. For all these cases, I mean, for all these genera of surfaces, including the torus, the length. Well, okay, the set of length of the closed geodesics determines the isometry type. So I said the set of lengths means all of them, not only the one and the next one. Maybe for the torus, the next one, I don't know. I have to think about it. The thing is that, so this is very important for what I will say later. And in fact, you may add here the word simple. Simple closed geodesics means without self-intersection. Without self-intersection. The embedded ones, the ones which embed injectively, the geodesics which are embedded injectively. So let me finish my sentence here. So we more or less understand that this is one-dimensional for the Teichmüller space of the torus. Now it's two-dimensional. This is two-dimensional, and in fact, a torus is generated. I come back to something which I said before, and now maybe you can understand more precisely. Is generated by two-generator group of translations a group of translation of the Euclidean plane. And this is here a Euclidean torus. This is what you are interested in, a Euclidean torus. And I can normalize. The one torus is the one generator is this translation by this vector, this horizontal vector. So this is 0, 1. This is the vector 0, 1. And here it's another vector v. So normalized so that the first vector is this vector 0, 1, and the second one normalized such that the first vector is the vector 0, 1, and the second vector v is in the upper half plane. So the second vector, if I mean, you can imagine that if I take this vector here and I take this symmetric vector here, then the two tori will be isometric. There's just a reflection which will give you the isometry between the group actions, and the tori will be isometric. So we forget about here. So this reminds you with something which is you know, I mentioned the name Teichmüller space here. I will write it again. You understand more or less now what this is. The Teichmüller space, well, of tori, of the torus. That is this surface here. Topological surface. The Teichmüller space of the torus is what? What should I write here? Somebody said something?
Upper half plane.
Yes. You understand? Your friend here said it's the upper half plane. Because I said that the Euclidean torus is generated by some group action. This vector is fixed, and the other vector moves in the upper half plane. The Teichmüller space is the upper half plane. So what is special with the upper half plane, in fact? I could say it's a half plane. Why do I care about the upper half? Because if I can make this, you see, I can say, instead of saying all this, I can say that I will normalize such that the first vector is this vector here, the diagonal vector, and the other vector is situated to the right with respect to orientation and so on, right? There's no special thing about the upper half plane. It's a half plane, so it's two-dimensional. The Teichmüller space of the torus is two-dimensional. This is the important thing we know now, right? It's two-dimensional, but the fact that it's the upper half plane is important, in fact, for something which I didn't tell you. We talked about Teichmüller space. You have a rough idea now of what it is. It is a space of metrics. It's the space of all Euclidean metrics on the torus. And upper half plane reminds you of what? Reminds you of the model for hyperbolic geometry, right? We said that the disk model and the upper half plane model. And it is a coincidence, but a very important coincidence, that this Teichmüller space is the upper half plane, in fact, comma, equipped with its hyperbolic metric So why am I talking about a metric here? Because I talked about Teichmüller space. I told you what is that this is a space, but I didn't tell you that it is a metric space, right? But I will tell you. No, I cannot because I need more than -5 minutes. That the Teichmüller space now here, in fact, is equipped with a metric called the Teichmüller metric. The Teichmüller metric, which I did not tell you what it is, but this is a very important part of what I want to do. I will explain to you what is this Teichmüller metric. It is not the Thurston metric. If I replace here the Teichmüller space equipped with the Thurston metric, this statement is not correct, because the Thurston metric of the torus is not the hyperbolic metric of the upper half plane. The Teichmüller space is still the upper half metric, the upper half space, but there are two different metrics: the Teichmüller metric and the Thurston metric.
But this Teichmüller metric is same as the Poincare metric on the upper half?
Yeah, this is what I'm saying here. Equipped with its hyperbolic metric. Yes. Next time I will explain to you what is this Teichmüller metric for the torus and for any surface of genus at least equal to 1. And we have a characterization of the Teichmüller metric of the torus. I will give you a characterization of the Teichmüller metric of surface of genus greater than 2. So I wanted to say something here. You see, there's something very important. Okay, we said it, but we did not. I think it was here, and then I erased it. We said that the isometry type of a Euclidean torus is determined by the length spectrum, by the set of lengths of injective closed geodesics. We wrote this after a discussion, you know. We said that the one geodesic is not enough. 2 geodesics, maybe, I don't know, but I know that the set of all closed geodesics, the set of all these lengths determine the torus. And this is something which is valid for any surface, in fact, and this is the important thing. Instead of a Euclidean torus, I want to say here, hyperbolic. I said that the surfaces which are other than the torus, surfaces of genus 2, 3, 4, 5, etc., of hyperbolic surface, let's say compact, and with or without boundary, doesn't matter, is determined by lengths, by the set of lengths of injective closed geodesics. This is something which I will explain and which I will insist on. Yes.
study all surfaces together in
No,
time?
no. You study one surface by for instance, surface of genus 2, but you study all the possible hyperbolic metrics on the surface. Yes, all of them together, but on a fixed topological type. Here we had a discussion on where the surface is the torus. It has a Euclidean structure, so things are more classical, say, more easy, and then there are many things which belong to number theory which arise here. Even there are things which belong to number theory. If you put a puncture on the torus, then the theory becomes different, and so on. I mean, this is why you have the theory with boundary, the theory without boundary, with punctures and boundary, surfaces of, when you study surfaces of infinite type, infinite genus, and surfaces with infinite genus with punctures, like, or surfaces of genus 0, like the sphere. We said that the sphere is not interesting in this kind of thing, but if you take the sphere minus a few points, it is a very complicated and interesting space. If you take the sphere minus a Cantor set, then this is also a surface of infinite genus, so it's also interesting. It has its proper theory. Yes, so this is a theory. I don't see who is talking. What did you say? Yes. What did you say? Yes. Yes, uncountably many. Yes, it could be uncountably many punctures. Yes.
Okay, so
Okay, thank you.
let's